A master-slave JK flip-flop is a type of bistable circuit that stores one binary bit. It is built from two JK latches placed in series. The first latch is called the master and the second is the slave. The master watches the input J and K while the clock CLK is low. The slave watches the master's output while the clock is high. This arrangement forces a change in the stored value only on one edge of the clock, usually the rising edge. The standard symbol looks like a normal JK flip-flop rectangle with the words MS inside, a data input J on the left, a data input K on the left, a clock input at the top, a Q output on the right, and a Q bar not Q output below Q. Think of the master-slave pair like a two-stage relay. The master stage prepares the decision, for example, should the light be on, while the slave stage actually flips the light on or off, but only when the relay switch, the clock, is in the right position. This prevents the output from changing more than once per clock cycle, which is the core idea of edge-triggered operation. The truth table of a master-slave JK flip-flop expresses what the next state Q plus will be for each combination of J, K, and the present state Q it is. JK vertical bar Q of T vertical bar Q plus. 0 0 vertical bar 0 vertical bar 0 no change. 0 0 vertical bar 1 vertical bar 1 no change. 0 1 vertical bar 0 vertical bar 0 reset. 0 1 vertical bar 1 vertical bar 0 reset. 1 0 vertical bar 0 vertical bar 1 set. 1 0 vertical bar 1 vertical bar 1 set. 1 1 vertical bar 0 vertical bar 1 toggle. 1 1 vertical bar 1 vertical bar 0 toggle. From the table we derive the characteristic equation that gives Q plus directly from J, K, and Q. Q plus equals J dot not Q plus not K dot Q. This can be simplified using Boolean algebra. Q plus equals open parenthesis J dot not Q close parenthesis plus open parenthesis not K dot Q close parenthesis equals open parenthesis J plus not K close parenthesis dot open parenthesis not Q plus Q close parenthesis distributive law equals J plus not K because open parenthesis not Q plus Q close parenthesis equals 1. However, the unsimplified form J dot not Q plus not K dot Q is useful because it clearly shows the three basic actions, set, reset, and toggle, and is the form used inside the hardware implementation. The equation also shows why the JK flip-flop is called a universal latch. By tying J and K to appropriate constant levels, you can emulate a D flip-flop. Connect J equals D, K equals not D, or a T flip-flop. Connect J equals K equals T. A timing diagram for a master-slave JK flip-flop focuses on two clock phases, Phi 1 clock low and Phi 2 clock high. While Phi 1 is active, the master latch is transparent. It sees J and K, and the slave latch holds its previous state. When the clock rises, Phi 1 ends and Phi 2 begins. The master now freezes its output and the slave becomes transparent, copying the master's stored decision to Q. Key timing parameters are propagation delay, TPD, the time from a valid clock edge to the moment Q stabilizes. In a master-slave device, this is roughly the sum of the master's internal delay plus the slave's delay. Race through, if the master's output were allowed to feed the slave during the same clock edge, the circuit could toggle more than once, a race. The master-slave arrangement eliminates race through by ensuring the slave only looks at the master when the clock is in the opposite phase. An everyday analogy, imagine a handoff relay race. The first runner master runs while the baton data is in his hand, the second runner slave stands still. At the exchange zone clock edge, the first runner stops, hands the baton, and the second runner starts running. Only one runner moves at a time, preventing the baton from being passed back and forth repeatedly within the same exchange. In the diagram you would see a clock waveform, a narrow Phi 1 low interval followed by a Phi 2 high interval. Q changes only at the rising edge, and the change appears after TPD, staying stable until the next rising edge. The internal circuit of a master-slave JK flip-flop consists of two edge-triggered JK latches connected in series. Each latch is built from a pair of cross-coupled NAND or NOR gates with J and K feeding the set-reset inputs through additional gating that is enabled by the clock phase. Master latch enabled when CLK equals 0 or when the inverted clock Phi 1 is high. Its internal gates receive J and K directly. The master produces an intermediate output Q sub M. Slave latch enabled when CLK equals 1 or when phi 2 is high. Its inputs are taken from Q sub m and its complement. The slave produces the final Q output. Because each latch is edge-triggered, the master captures the J/K values on the falling edge of the clock, and the slave transfers that captured value to the output on the rising edge. The schematic looks like two rectangles side by side, each labeled JK latch, with a clock-inverted line feeding the master and a non-inverted line feeding the slave. The output of the master is wired to the data inputs of the slave, and Q of the slave feeds back to the master's reset line to keep the circuit stable. This construction guarantees that any change in J or K within the clock period does not affect Q until the next active clock edge. Flip-flops must satisfy setup, hold, and clock to QTCQ timing constraints for reliable operation. Setup time T setup, the minimum time that J and K must be stable before the active clock edge. Hold time T hold, the minimum time that J and K must remain stable after the active clock edge. Clock to QTCQ, the time it takes for the output Q to reflect the new state after the clock edge. Example calculation: assume a master-slave JK flip-flop with the following specifications from its datasheet. T setup equals 2 nanoseconds. T hold equals 1 nanosecond. TCQ equals 3 nanoseconds. TPD equals 4 nanoseconds propagation through master plus slave. You plan to run the circuit at 50 MHz period T equals 20 nanoseconds verify timing. 1. The data must be stable at least 2 nanoseconds before the rising edge data window starts at T equals 0 nanoseconds, edge minus 2 nanoseconds equals minus 2 nanoseconds. 2. After the edge data must stay stable for at least 1 nanosecond data window ends at T equals 0 nanoseconds plus 1 nanosecond equals plus 1 nanosecond. Thus, the usable data window is from minus 2 nanoseconds to plus 1 nanosecond around the edge, a 3 nanosecond window, which is well within the 20 nanosecond clock period. 3. The output will be valid at T equals 0 nanoseconds plus TCQ equals 3 nanoseconds after the edge, and will settle fully by T equals 0 nanoseconds plus TPD equals 4 nanoseconds. That means the next edge 20 nanoseconds later will see a stable Q. If you wanted a faster clock, say 200 MHz period equals 5 nanoseconds, the data window would still be minus 2 nanoseconds to plus 1 nanosecond. But the next edge arrives at 5 nanoseconds, leaving only 1 nanosecond for the output to settle 4 nanoseconds less than 5 nanoseconds still okay. However, the margin becomes small, so you would need a flip-flop with smaller TCQ/TPD for higher frequencies. Master-slave JK flip-flops are often used as frequency dividers and counters. Because of their toggle capability, J equals K equals 1. Frequency division toggle mode. Connect J and K together and feed them with logic 1. Each rising clock edge toggles Q, so the output frequency F out equals FCLK divided by 2. Cascading n such flip-flops divides the clock by 2 to the n. Example: 3 cascaded JK master-slave flip-flops produce FCLK divided by 8. Binary counter. Connect the Q output of each stage to the clock input of the next stage as a ripple counter. For a 4-bit counter, the truth table of the whole system counts from 0000 to 1111 and then wraps to 0000. Decade 0 to 9 counter. Use 4 JK master-slave flip-flops Q0 to Q3 and add a reset circuit that forces the counter back to 0000 when the count reaches 1010.10. The reset can be generated by ANDing Q1 and Q3 both 1 at count 10 and feeding this signal to the asynchronous reset inputs of all stages. When the count hits 1010, the reset pulse clears the flip-flops, so the next count starts again at 0000, giving a modulus 10 counter. Real-world analogy: think of the flip-flop as a gear that turns half a turn for each input pulse. Stacking gears makes the overall rotation slower, just like dividing frequency. The decade counter is like a mechanical odometer that rolls over from 9 back to 0. Explanation: below is a quick comparison of a master-slave JK flip-flop with other common flip-flops. Feature: master-slave JK, simple JK level triggered D flip-flop T flip-flop. Edge triggered, yes rising edge, usually level triggered susceptible to race through yes yes. Universal functionality can act as D, T, or SR by wiring J/K appropriately. Same, but timing may be ambiguous due to level sensitivity. Only stores D input, toggles on T equals 1. Setup hold requirements, defined relatively tight, may need additional gating to avoid glitches. Usually easier single data line, similar to JK when used as T. Race-through protection, built in master-slave separation, not inherent, needs external clock gating. None needed, none needed. Typical use, synchronous counters, frequency dividers, state machines where both set and reset are needed. Simple latch-type designs, low-speed applications, data registers pipelines, simple toggle counters. Advantages of master-slave JK: reliable edge-triggered operation, no race-through, flexible functionality. Limitations: more transistors than a D flip-flop, higher propagation delay, slightly larger area. A simple JK level triggered is smaller and faster, but can change output multiple times during a clock pulse, which is undesirable in high-speed digital designs. Explanation: here are 3 typical exam-style problems and a brief strategy to solve each. Number 1. Design a 3-bit synchronous up counter using master-slave JK flip-flops. Connect 3 JK master-slave flip-flops Q2, Q1, Q0. For a synchronous design, drive all clock inputs with the same system clock. Derive the J and K inputs. Each stage toggles when all lower order bits are 1. Thus, J0 equals K0 equals 1, always toggle. J1 equals K1 equals Q0. J2 equals K2 equals Q0 and Q1. Implement the required AND gates and feed them to the respective JK inputs. Verify with a truth table that the count sequence 000 to 00, 1 to 010 to 111 to 000 is obtained. Number 2. Calculate the maximum clock frequency for a master-slave JK flip-flop with T setup equal 1.5 nanoseconds, T hold equals 0.5 nanoseconds, TCQ equal 2 nanoseconds, and TPD equal 3 nanoseconds. The minimum clock period Tmin must satisfy Tmin greater than or equal to T setup plus TCQ plus T margin. The margin is often taken as the larger of T hold and any internal timing skew. Conservatively use T hold equals 0.5 nanoseconds. Tmin equals 1.5 nanoseconds plus 2 nanoseconds plus 0.5 nanoseconds equals 4 nanoseconds. Maximum clock frequency, Fmax equals 1 divided by Tmin equals 250 MHz. Number 3. Given a JK master-slave flip-flop, prove that connecting J equals D and K equals not D makes it behave exactly like a D flip-flop. Substitute J equals D and K equals not D into the characteristic equation. Q plus equals J and not Q plus not K and Q equals D, and not Q plus not D and Q equals D, and not Q plus D and Q equals D, and open parenthesis not Q plus Q close parenthesis equals D times 1 equals D. Therefore, the next state equals the D input, which is the definition of a D flip-flop. Show the timing diagram. On each rising edge, Q follows D. Solution strategy. Write down the required function, count, frequency division, etc. Translate the function into Boolean expressions for J and K using the characteristic equation. Simplify the Boolean expressions with Karnaugh maps or algebra. Draw the gate-level schematic. Add necessary clock distribution and verify with a truth table. Finally, check timing constraints using the datasheet values to ensure the design works at the intended clock rate.